Hello, fellow. My name is James Owusu-Appiah, and I believe in innovation and doing things differently. This video has been prepared for you to guide you through some well-known concepts that will aid your studies and preparations towards exam. Due to COVID, we cannot meet in person to discuss, so I hope this video finds you well and helps you achieve excellence. Thank you.
Welcome to JOA Reviews. My name is Francis and I'll be taking you through Phasors today. The first question that comes to mind when you hear of a term is, what is this particular term? In this case, what is a phasor and what am I even going to use a phasor for? Why do I need to learn it? To answer these two questions, let us go back to what we know already. We see from Ohm's law that V is equal to IR. You apply a voltage across this particular resistor, the resistor in this diagram. We can represent it here. You apply a voltage across it, and then the current through it can be given by V over R from Ohm's law. Very easy, and you can do it. But it becomes more complicated or kind of very difficult when we have my younger brothers in circuit, the inductor and the capacitor. They behave kind of differently from the resistor. They don't charge, their currents and their voltages don't follow each other. There's a phase shift between them. Well, if I say a phase shift, we are going to understand that in just a moment. So let's assume you are applying this particular wave Vm, which can be represented by Vm sine omega t, across this resistor. When we apply this across the resistor, we say they follow each other. So this is what you are going to get. While the voltage is rising, the current also rises in that manner. They just follow each other. So we say they are in phase. There's no phase shift between them. There's no, one doesn't delay while the other moves away from it. They all start at zero, rises to the top at the same time, and then falls back to zero at the same time. So let's say zero goes to their maximum value at the same time, and then comes back to zero at the same time. So there's no shift between the one, doesn't go and leave the other. But it becomes different when you apply the same Vm sine omega t voltage. I mean, a voltage that varies with time, a sinusoidal voltage that varies with time. You apply it across a capacitor or an inductor, and this is how they behave. For an inductor, due to magnetic reluctance, so when you apply a voltage to an inductor, you see that the voltage kind of goes and then leaves the current because there was no force applied to it. You apply this particular voltage to it, and you realize that the current doesn't begin at the same time as the voltage. So you realize at this point in time the voltage has reached its maximum, but the current is still not at its maximum. So we see there's a phase shift between them. This phase shift is just caused by inertia. In this case, I would say magnetic inertia. You do that same thing across a capacitor. You apply the same voltage across the sinusoidal voltage varying with time, which we decided to represent by Vm sine omega t. We apply it across a capacitor, and this is how it's going to behave. The voltage starts from zero. Well, the current actually just starts from one. I mean, the current always leads the voltage. So while the voltage is at zero, the current has already reached its maximum. So we are going to say the current leads, the current leads the voltage by an angle of 90 degrees. When you do this in your labs, you use the digital oscilloscope, connect your circuit, and apply a sine wave across an inductor and a capacitor and observe them on the screen. You are going to appreciate this for yourself. So analysis of this circuit, let's assume we always have to draw this wave, or we always have to draw this wave. Like how are we always going to draw this wave? No, that is not going to work for us. So the best thing we can do is to implore something, go into something, use something. We always try to make things easier for ourselves. So that is why we go to implore phasors. Phasors, what are phasors? Phasors, I just say they are vector representations of the steady state of this voltage. So we have the sine Vm sine omega t that we have been using all this while, a voltage, sinusoidal voltage given by Vm sine omega t. We apply it, and you always will not be willing to be drawing this, always be drawing this in our books for analysis and other things. It's not convenient, not be convenient on our behalf. So what we are going to do is to use phasors. Phasors, we are just going to represent the steady state values of this particular voltage, the Vm sine omega t. We are going to represent it just by this voltage. We are going to represent it by a vector, and you always know that vectors always have magnitude and direction. So a phasor, they are used to represent, just used to represent sinusoidal quantities to avoid drawing the sine wave always. It's not convenient, you can't always be drawing the sine wave. So uh, phasors are just something like vectors. So let's say a vector is represented by A, B. They have magnitude and direction. So if you have this, you can put it in the form of a phasor this way. And the length of this line, the length of this particular line I have drawn here actually represent the magnitude of the voltage of, I mean, whatever sinusoidal quantity you are talking about or you are considering. And then the angle between the angle here. So we have an angle here, say phi. So the angle between it just represent the phase relations between the two, between the voltage and the current, or whatever quantities you are trying to analyze at that particular point in time. And we talk about some terms, a phasor being in phase, and then two phasors being in phase, and then two phasors being out of phase. When we say phasors are in phase, then they point in the same direction. There's no phase shift between them. So let's assume we have a voltage source this way, then, and then we have its current also here, I. Here, there's no shift between them. They are always following each other, and that is what happens in a resistor. They always follow each other. But in an inductor and in a capacitor, we would always have this, the capacitor, and then we have the inductor. This is how their voltages and currents behave. There's a phase shift between them. Always, I mean always. So let's try to solve some questions using phasors. In the first example, we say a 50 Hz source having RMS voltage of 240 volt delivers a current of 10 ampere to a circuit. So the 240 volt source, so the RMS is just 240, and then IRMS, the RMS value of the current is what? 10 ampere. These two values have been given to you, and you are supposed to represent them in the form of a phasor. But in the question, they are saying that current lags the voltage by 30 degrees. So lagging and leading, so let me use this time to explain the lagging and leading. So we are going to take the voltage as the reference. You can decide to take the current as the reference, and it's up to you, but you should always consider the fact that one has been stated to be leading or lagging the other. So be careful if you are using the current as the reference or the voltage as the reference. It doesn't matter, but be sure to obey these rules. So for me, I'm going to use the voltage as the reference here. So this is the VIN, and it has what, an RMS value of 240 volts. And the current has a value of what, an RMS value of 10 ampere. So it has an RMS value of 10 amperes, and lag, so for lagging, it's in this direction. So going to the right, going towards the positive y-axis, it leaves, and then coming away from it, getting to the negative y-axis, we say it is lagging. So we have a 240 volt source and then a 10 ampere current, and this is the phasor diagram that can represent them. So you can place the 30 degrees in here to show the phase relation between the two of them. And the second question, the B part, is saying express the voltage and current as functions of time. To do that, let me first of all erase everything. We always know that our V is always represented by V M sine omega t plus Fi. And in this particular question, we've been given the RMS value of the voltage. So we know that Vm is root 2 times the RMS. So root 2 times 240 is just 240 root 2, and that comes in here. And then the phi over here, the phi we have in this particular instance, this phi will just be depicted by the angle that we are considering. But in this case, we are talking about the voltage being the reference for us. So if it is the reference, then the phi should actually be a 0 degree. So this can just be represented as V is equal to 240 root 2 sine omega t plus a 0. And you can also notice that the omega is just 2 pi f, is 2 pi times the frequency. This can be proved from your high school physics. So omega is just 2 pi times the frequency. In this instance, we've been given the frequency here to be 50 hertz. So 50, and that gives you 100. So this whole thing just becomes, let me take the eraser, and then this just becomes 100. This is 100 pi. So 240 root 2 sine 100 pi t plus a 0. So plus a 0 actually shows nothing, so we can take it out of the equation, and it just becomes this 240 root 2 sine 100 pi t. That is the voltage as a function of time. And we can apply the same thing to the solution for the current as a function of time. So omega we knew to be 2 pi f, and the frequency here is still the same, so that is 2 pi times 50, and that will give you 100 pi. And we also know that V, or what, Im, in this case we are considering the current, so it is I. So Im is root 2 times I RMS, and that will give you root 2 times, in this case it is 10, so that's just 10 root 2. So we have our Im, and the next thing we are going to look for is the phase shift, the angle between them, so by 30 degrees. So to represent this, I is Im sine omega t plus Fi, the phase shift in this instance, and we just fix in this, but these values, the values we have already, and we are going to get Im we have found to be 10 root 2 sine omega t. Omega we have found in our previous instances to be this 100 pi, so just place it in the 100 pi t, and then plus, in this case we are saying the current lags the voltage by 30 degrees. So if it is lagging, then that means it is negative. If you are coming from the voltage, then the current, you have to go in the negative direction. So this plus should just become plus minus 30. So plus minus 30. And plus minus can just be written as just a minus. So this is it. Thank you.